You know, when you see a jet engine spinning thousands of times a minute, have you ever stopped to think about how it doesn't just, tear itself apart? Or how your car's engine can run so smoothly at crazy high speeds? Well, the answer is this incredible, almost invisible piece of engineering that's designed to tame some seriously violent forces. So let's pull back the curtain and see the physics that makes it all work. Okay, we've all been there, right? You throw a load of laundry in, and a few minutes later, it sounds like the machine is trying to punch its way through the wall. That insane shuddering and thumping, that runaway vibration is the exact problem engineers have to solve, just on a much, much bigger and more dangerous scale. It's the perfect everyday example of a system that is completely out of balance. And the solution to this whole mess? Well, it has a name: balancing. It's pretty much the science of designing and tweaking machinery to cancel out all those disruptive forces. The main goal is to get things running so incredibly smooth that you barely even know they're moving. But to really get how the fix works, we first have to understand the problem. Right, so to figure out the solution, we've got to play detective for a minute. What in the world is actually causing that violent wobble? Let's go track down the culprit. And this right here is why balancing is so absolutely critical. See, as our machines have gotten faster and faster, even the tiniest little imperfection in a spinning part creates these huge, powerful forces. And we're not just talking about annoying noises. This stuff puts immense stress on bearings, it causes super dangerous vibrations, and it can literally tear a machine apart from the inside out. So this isn't about making things quiet and comfortable. It's absolutely essential for safety and performance. So where does this crazy destructive force actually come from? Well, the answer is a really fundamental principle of physics that honestly you've probably felt your entire life, even if you didn't know what it was called. This diagram here shows the whole principle in a nutshell. Anytime you spin a mass around a central point, it generates a force that wants to pull straight outwards. Just think about swinging a ball on a string, right? You can feel that tug trying to fly away from you. That is centripetal force, and it's happening in every single thing that rotates. Now, here's the key. The force itself isn't really the problem. The problem, what we call the disturbing force, is created when the object's center of mass isn't perfectly lined up with the axis it's spinning on. If the weight is just a little bit off center, that outward pull starts yanking on the entire shaft, trying to drag the whole machine along with it. That's where our wobble comes from. Okay, so if you've got this off-center mass pulling the machine in one direction, how do you stop it? Well, the engineering solution is actually kind of elegant and simple. You just pull it back in the exact opposite direction, with an equal amount of force. You literally fight fire with fire. This image shows the simplest way to do it. You see that disturbing mass up top, the one labeled M1? That's our problem. It's pulling the whole system off center. So to fix it, engineers just add a balancing mass, M2, on the exact opposite side. The goal is super simple. Make the outward pull from the new mass perfectly cancel out the pull from the original. And this all boils down to a beautifully simple rule. For this to work, the first mass times its distance from the center has to equal the second mass times its distance from the center. It works exactly like a seesaw, you know? A really heavy person sitting close to the middle can be perfectly balanced by a lighter person sitting way out on the end. Same idea. But of course, it's not always that easy. What happens when the forces are pulling equally, but they're pulling from different spots along the length of the shaft? Suddenly, stopping the wobble isn't enough. You also have to stop the whole thing from twisting itself into a knot. And this brings us to a really important difference. There is something called static balance. That's when all the outward forces cancel out, so the shaft won't wobble side to side. But it might still try to rock back and forth, creating a twisting force. Imagine pushing on opposite ends of a steering wheel at the same time. The forces are balanced, but the wheel still turns, right? That's the twist. For a machine to be truly, perfectly stable at high speed, it needs dynamic balance, where both the wobble and the twist are completely gone. So how do engineers get to that perfect dynamic balance? Well, as the source material puts it, the solution is usually to use two balancing masses, but placed in different locations or planes along the shaft. This gives them the power to counteract not just that side-to-side wobble, but the twisting motion too. And these two diagrams show exactly how that works. So look at the picture on the left. The blue problem mass is sitting between the two balancing masses. To stop the twist, the balancing weights are put on the same side. Now look at the diagram on the right. Here, the problem mass is on the outside. To fix that, the balancing masses have to go on opposite sides to cancel out that twisting force.
It really shows how engineers have to calculate not just how heavy the counterweights are, but exactly where to put them.
Okay, so balancing one mass is one thing. But what about something like a car engine's crankshaft? You've got pistons and rods creating forces all over the place. This is the real final boss, balancing a whole symphony of different masses at once.
And yeah, this slide shows you just how complicated it gets. In a real machine, you've got a bunch of masses, M1, M2, M3, all at different angles, different distances, and each one is pulling the shaft in its own unique direction. I mean, it looks like total chaos, but engineers have this incredibly methodical way of taming it. The solution is this really elegant four-step process. First, they identify every single unbalanced force. Then, they break each of those messy, angled forces down into simple up and down and left and right parts. After that, they just add up all the left-right parts and all the up-down parts to find one single overall unbalanced force. And finally, all they have to do is add one balancing mass that creates a force that's perfectly equal and opposite to that one. It's a method that turns absolute chaos into perfect mathematical order.
And this is why it all matters so much. This whole process, this hidden science of balancing, is what allows our entire modern world to function. It's what keeps your car from shaking itself to pieces on the highway. It's what lets a massive turbine in a power plant spin for years without failing. It is quite literally the physics of smooth, safe, and powerful operation.
So the next time you see a ceiling fan spinning without a hint of a wobble, or you feel the smooth power of a car engine, you'll know about the incredible engineering that's at work behind the scenes. And now that you get the principle, what else can you spot? I mean, think about it. Computer hard drives, bicycle wheels, even a simple spinning top. The world is just full of objects that completely depend on this idea of perfect balance.